In this video, we take a look at an application of the derivative that has a more theoretical feel to it, right? So recently we've done a lot of applications that talk about optimization or related rates, and those you can always find lots of physical, like real world, quote unquote, real world applications or problems that result in us having to use the derivative in a particular way. In this video and in the next video, we're going to look at two results that are more theoretical. And these are results that you may find yourself using in more advanced, not just math courses, but other technical courses that require a little bit more of a theory. So this theorem is referred to as Rolle's theorem or Raleigh's theorem. I remember when I was a student, my professor would refer to it as Raleigh's theorem. So I'm going to go ahead and refer to it in that way, right? So let's actually start with a statement of the theorem, and I will give you a relatively brief proof of the theorem, and then we'll look at a few examples, right? So here is our theorem, and this is Raleigh's theorem. And it basically it requires two things. It says suppose f of x, so we have a function. So suppose f of x is continuous on the closed interval, right, and differentiable in the open interval. So notice the difference between these two intervals. Here the endpoints are included, here the endpoints are not, right? So we have a function that's continuous on the closed interval, differentiable in the open interval, if one more hypothesis is needed. If f of a is equal to f of b, so this is saying that the function value at the endpoints are the same, right? So then there is at least one c in the interval a to b, right? The open interval a to b, such that f prime of c is equal to 0, right? So it's basically saying if the function has these three ingredients, it's continuous on the closed, differentiable in the open, and if the function values at the endpoints are equal, then somewhere inside the function has to have a stationary value. So there has to be at least one point where the derivative is equal to 0. There could be many more, right? But there has to be at least one. All right. Well, let's look at a pretty concise proof, and this proof actually uses the extreme value theorem. So this is what we know. By the extreme value theorem, right? Because we have a continuous function on a closed interval, f of x attains an absolute maximum, right? And absolute minimum on this interval, right? So somewhere on this interval, right? Remember that's what the extreme value theorem guarantees, your EVT. If you have a continuous function on a closed interval, then it has to have an absolute max and an absolute min somewhere on that interval. Now, there are two possibilities. If the function is actually constant, so if f of x is constant on this entire interval, then it means both the min and the max are the same. It's that same constant value. But moreover, we know that the derivative of any constant is equal to 0. So then f prime of x is equal to 0 for all values of x in this interval, right? So for all x in this interval. So not only do we have 1 or 2, but it would be for every value of x. So therefore, that shows you that, okay, if the function is constant, we get not just 1 or 2, but we have lots of points at which the derivative is equal to 0, because what you have is a horizontal line, and the slope is always equal to 0, right? Well, what if the function is not constant? Well, if f of x is not constant, but we know that f of a is equal to f of b, then it means that the endpoints cannot be the location of the absolute min or max, right? Because the function is not constant, so your max and min can't be the same. So if the function is not constant, but we know that the function value at the endpoints are the same, then the absolute, I'll say, extrema must occur at critical values, right, inside the open interval, right? Remember, again, as far as what the extreme value theorem tells us, and in fact another theorem which we haven't really stated, Fermat's theorem, it basically says if you have a continuous function on a closed interval, the absolute min and max must occur at either endpoints or at critical values inside, right? But what do we know about these critical values? Since the function is differentiable, right, at every point in the open interval, then the derivative always exists, right? So since f prime of x always exists, in this open interval, then think about critical values. What defines a critical value? Either the derivative is equal to 0 at some point, or the derivative does not exist. But because we know the derivative always exists, then there is only one other possibility. So therefore, f prime of x must be equal to 0 at some point inside this interval, right? So at some point in our open interval, right? And that's what the theorem says. So in both cases, whether the function is constant or not, and it's one of the two, right? Assuming that we have a continuous function on a closed interval and it's differentiable everywhere inside the interval, and the endpoints are equal, then there has to be at least one point where the derivative is equal to 0, right? And that's our QED, right? So graphically, what does it mean? Well, it basically means this. If we're drawing a continuous function, so let's say this is going to be f of a and f of b, so they're going to be equal, and I'm going to start the function at that point. So there's our a, there's our b. It says no matter how I draw, as long as I avoid sharp corners and I go up and down, so I start basically where I started in terms of the y value. So I start at this y value, I go up, down, as long as I avoid sharp corners, and I come back here. And what this means is there has to be at least one point where the tangent line to the graph is horizontal. Now we can see we have lots of them here. Here is a point where the tangent line is horizontal. Here's another point where the tangent is horizontal, and there, and there, and there, and so forth, right? So that's basically, it guarantees, right, the existence of these stationary points on a particular function. Now, what it's not saying is that this is the only scenario that will lead to these stationary points. No, it's not saying that. It's saying under these conditions, you are guaranteed. It's not an if and only if statement. It's just basically saying if we have continuity, if we have differentiability, if the function value at the endpoints are equal, then somewhere inside the interval, the tangent line will have to be horizontal. All right. Okay, so let's take a look at a couple examples of this. And what we're going to do with these examples, we're basically going to go through just a few functions and check to see if the theorem applies. And if the theorem does apply, we are going to find these special points inside the interval, right? So we're basically going to do this. So we'll answer this question. Does Rolle's theorem apply? And then if so, find the values guaranteed. Right, so guaranteed by Rolle's theorem. All right, so let's get the first one. So here's our function, f of x, and it's equal to 1 minus x to the 2/3 power. And here's our interval, -1 to 1. All right. Well, let's think closely. Think about this function. So x to the 2/3, that's basically saying that you have the cube root of x squared, right? Now, the square function or parabola is always continuous. The cube root function is always continuous. Therefore, 1 minus the cube root of x squared is always continuous, right? So that's at least we see that we have a continuous function. Let's go ahead and check everything. Now, the first things I will check the endpoints just to see if in fact f of -1 is equal to f of 1, right? So let's start with our f of -1. Now, if I use this form of the function, it's 1 minus the cube root of -1 squared. So that's 1 minus the cube root of 1, which is 1 minus 1. That's equal to 0, right? Let's see what happens if we plug 1 in. So if we evaluate this function at 1, then it's going to be 1 minus. Now if I use the original form of the function, it's 1 to the 2/3. 1 to the 2/3 is equal to 1. 1 minus 1 is 0. So this implies that yes, f of -1 is equal to f of 1, right? So we have that the function values are equal at that endpoint. Now let's check continuity. Well, I already stated that, this function, so f of x equals 1 minus the cube root of x squared is continuous, not just on this interval, but in fact for on the entire real line, but I'll go ahead and state it since this is the interval under consideration. So this function is continuous, right, on this closed interval. Now let's check the derivative, right? Now to differentiate this, I'm going to go back to this form and use our power rule. So f prime of x is equal to, well, the constant differentiates to 0, constant multiple of -1, so bring down the negative sign. Now apply our power rule to this, and I'll have 2/3 x to the, now 2/3 minus 1, that's -1/3. Well, I can rewrite this, again, just so that I'm very clear as to what the operations are involved here. I'm going to write this derivative so that I don't have negative exponents. Well, this is equal to negative 2 over 3 to the cube, or 3 times the cube root of x, right? But we can now see a problem. Now that we have this cube root of x in the denominator, at x equals 0, which is inside this interval, this derivative does not exist, right? So this function, this derivative I should say, or f prime of x, does not exist at x equals 0. You try to plug 0 into this derivative and you're going to get something that does not exist. It's undefined. So therefore, the original function is not differentiable in the open interval -1 to 1, right? So it's not differentiable in this interval. Hence, Rolle's theorem does not apply. So there is no guarantee that this function will have a stationary point or stationary value on this interval. So hence, Rolle's theorem does not apply, right? So, I mean, and even if the theorem doesn't apply, it's still a very worthy exercise to go through and make sure we understand the properties and understand, how to identify, when functions are continuous. That's why we did, several sections on continuity. And then talking about differentiability. When does a derivative equal to 0? When is a derivative undefined? All those things are coming together in this particular problem, right? Okay, let's look at another function here. Let's take something like, so f of x is equal to x cubed minus 2x squared minus 8x, and the interval now is -4 to 2. All right. Well, what do we have here? Well, we have a polynomial, right? So we have a polynomial. And what do we know about polynomials? Well, polynomials are always continuous and they're always differentiable. So, but don't overlook the endpoints, right? So let's check those endpoints. So let's try f of -4. Well, so let's do what the function says. So this is -4 cubed minus 2 times -4 squared minus 8 times -4. So -4 cubed, that's -64. And then what do we have here? This is 16 times -2, so that's -32. And then here we have a plus 32, so -64. Right? So at the left endpoint of this interval, the function has a value of -64. Well, what about at the right endpoint? Well, let's see. Let's plug 2 in. So this is 2 cubed minus 2 times 2 squared, and then minus 8 times 2. So 2 cubed is 8, 4 times 2 is 8, and then we have a minus 16. Oh, so take a look at this. So now the endpoints are not the same, right? So I don't even have to, we already stated, right, that the function is continuous and differentiable everywhere for all values of x, but that's irrelevant now because at the endpoints the function values are not the same. So since f of -4 is not equal to f of 2, Rolle's theorem does not apply, right? Again, so we can't use Rolle's theorem to justify or to conclude that this function has to have a stationary point somewhere between x equals -4 and x equals 2. Could we use some other means? Sure, we just can't use Rolle's theorem, right? All right, let's try another one. let's take a look at, so what are we at, number 3. So let's say our function is x times x minus 1 squared. So there, and then let's say the interval now is from 0 to 1. All right. Well, again, let's check our endpoints because those are probably the easiest things to check, right? That's simple algebra. So if we evaluate the function at x equals 0, we're going to have 0 times 1, so that's equal to 0. If we evaluate the function at 1, we're going to have 1 times 0 squared, which is 0. So therefore, f of 0 is equal to f of 1. That's good. And now this is still a polynomial. It's a polynomial in factored form, but we can state that since f of x is a polynomial, right? Then f of x we know is continuous. So it's going to be continuous on the closed interval and differentiable in the open interval, right? So no sharp corners, nothing like that on our nice polynomial. So finally we get a situation where Rolle's theorem does apply. So therefore, Rolle's theorem applies. Finally, I guess the third time's the charm. So it means that at some value of x between 0 and 1, this function, right, has to have at least one stationary point. So there has to be at least one point where the derivative is equal to 0, right? So let's now find this derivative. Now, the way the function is written, since it's written in factored form, we would have to use our product and our chain rules. If you wanted to, for instance, you could actually pause the video and maybe expand and distribute the x and then use a bit of algebra to rewrite the function, then take the derivative, and then see if we end up with the same derivative. That would be a nice little exercise, right? But I'm going to go ahead and leave it in this form and compute the derivative, again, using the product and chain rules, because I have my composite there and my product there. So using our product rule, we'll have 1 times the quantity x minus 1 squared plus x times, and then bring down our power, keep the inner function, subtract 1 from the power, and then multiply by the derivative of x minus 1, right? So this is our product rule all here. If you want to, I can go ahead and highlight that for you. So this is using the product rule, and then right here we used our chain rule. Now, since we are going to be trying to figure out the value of x that makes this derivative equal to 0, it's actually helpful if we factor, right? And so instead of me foiling things out, so here is the factored form of the derivative. Now I can factor out the quantity x minus 1. And then that leaves a factor of x minus 1 there. And then what's left from this term? Well, I have a 2 and I have an x. I've already factored out the x minus 1, so I don't need to worry about that. And of course, this 1 doesn't change that term, so I end up having a plus 2x there. All right. So if I simplify what's in the square brackets, I have my derivative in factored form, which is helpful. When you think of a lot of the work that we've done recently with derivatives, having it in factored form is really helpful, right? So where is this derivative equal to 0? So where is f prime of x equal to 0? Well, we have it nice and factored. So if we set that equal to 0, then what's going to happen? Well, either x is equal to 1 or x is equal to 1/3. So which of these? It's actually, we can't use this value because this is one of our endpoints. Raleigh's theorem says that the value of x that's guaranteed is somewhere in the open interval. So it's not this, right? So since I'll say C has to be in the open interval 0 to 1, this implies that the number that's guaranteed by Raleigh's theorem is 1/3. So C is equal to 1/3. Right? So even if the endpoints end up being one of the, like stationary values, we can't use that as a value that's guaranteed by the theorem. It has to be in the open interval. Neither of the endpoints can be used. It has to be some number strictly between 0 and 1. And in this case, it ends up being 1/3, right? So there's our Raleigh's theorem. Pretty useful result, and I almost guarantee you that at some point in more advanced courses, you may rely on this result to maybe prove some other result, or to derive some other important property that functions can have. All right. Well, hopefully you found that interesting, and those examples helped kind of highlight what the theorem is saying and how you can use it. And for our next theoretical application of the derivative, why don't you tune into the next video? See you then.